Hello, everyone. This is your teacher, John Grubbs here. This is our GoToMeeting for Monday morning, August 31st, our first GoToMeeting of this new week, and just sent you the announcement just in the last few minutes. Actually had technical difficulties trying to set up this GoToMeeting from my home computer yesterday. That just wasn't going to happen, and it's some of the requirements of the system and all. We've got a license here at the college campus to use this program, and so there's some limitations with me trying to use it from home apparently, and maybe I can find a way around that, but I couldn't yesterday. So anyway, the announcement is out there now, and if you're not able to watch this live with me, it will be posted up, of course, after the actual live event. Early this afternoon, it'll be posted up, available to everyone to watch the recording of this. And a little overview of where we are and where we're going before we start talking about the specific lesson of the day, the section 1.3 in the textbook about functions. We are on course now to, as a regular weekly routine, have a GoToMeeting on Monday mornings at 11 o'clock and Wednesday afternoons at 3 o'clock. So we're going to have live meetings twice a week on this schedule, unless there's reason to interrupt that schedule. So each week you can expect to have a live GoToMeeting, which you can sign into and participate in and ask live questions to be answered right during the meeting, each Monday at 11 and each Wednesday at 3 in the afternoon, so twice a week. And these meetings will cover the sections of the course, the topic material in each section. We will also use these sessions to review for a test and even give some directions about lab activities and such as that. But for now, our schedule is to have 2 of these each week, 11 o'clock Monday mornings and 3 o'clock Wednesday afternoons. So let's go ahead with this one now. The 1.3 section in your text is about functions. It's just a general introduction to functions. What is a function? What is function notation? What do we mean by the f of x notation? And I trust everyone has seen this before. You've covered this in some measure previously, but we're going to actually start right at the beginning, the very basics and beginnings of the idea of what is a function. And this idea itself is quite abstract, actually. It's a very, it's a concept that doesn't just lend itself to a simple discussion. Coming at it from several different directions, explaining it from several different angles. I trust it'll make more sense as we go along, but honestly, it's going to make the most sense of all after you get in and do actual problems yourself on your own, do your own homework problems and all. The concept will solidify with you after you actually do this. So let's look at due dates too before we go any farther. 2 homework assignments are due for you this week, and that's actually all that is due this week is 2 homework assignments. The 1.3 homework assignment is due tomorrow evening, Tuesday, September 1st at 11:59, and the 1.4 homework is due Thursday evening, September 3rd at 11:59. So 2 homeworks due this week. So all we have this week is the 1.3 and the 1.4, and both due at 11:59 on those 2 evenings, Tuesday and Thursday. Our Wednesday afternoon GoToMeeting, I'm expecting at this point, that's going to be about the section 1.4. We'll be preparing for that, about graphs of functions. So I see we have somebody signed on here. That's terrific. What I'm going to do once again, as I've learned we need to do this, I'm going to mute the microphone. So any questions you have, please just type them in the chat box so that we can address your questions if you have any throughout this presentation. So I'm going to mute the microphone now. And Also, something else I need to tell you, I've got a little technical difficulty right here, even in my office at Western Piedmont this morning. For some reason, my iPad is not interfacing with my desktop PC. Normally it works just fine. I've had a few glitches before, but most of the time it works. But right now, I can, for some reason, not get the images on the iPad to project up onto the screen so you can see them, which means that this morning, I'm not going to be able to actually work out as I do using the iPad screen sort of like a whiteboard and using my finger as the marker to do problems together. Instead, I'm going to be using the textbook on screen and go through the textbook and talk with you and answer any questions you have, but talk with you and explain various concepts and all as best I can just verbally. Unfortunately, do not have the iPad screen to work out problems individually with you this morning. I wish I could, but it's just not working for some reason. So I am going to, at this time, switch over to the text. And this is the section 1.3 in your text, starting on page 97. If you have either the online text or the hard copy, it's page 97, Introduction to Functions. And let's talk about this. What is a function? That's a major question. What is a function? It's actually it's a rule that causes values from one set to translate over or to map to values in another set. So you've got these typically two sets of values, or generally values, but they could be other things too. Could actually even be names of things, but we're going to work with numbers primarily. The function itself is a rule which maps things from one of the sets to the other set. And in math, generally what we have is, for instance, two variables, the variable x and the variable y. And if we think of the variable x as being the input variable and the variable y as being the output variable, the function then is a rule, typically a math formula, that converts all the numbers in the original set, set A, which also we call the domain of the function. The function then is the rule that translates the values from the domain set into the set of values for the output, which is the range set. So there's two sets of numbers, let's say, the domain set and the range set. And we're always going from the domain to the range, never the other way around. Where the function always takes values from the domain set. Those are the input values. You apply the function rule to those values, and for each of those values then there is a corresponding output value in the range set. Because we always start with the domain set, the input values, these values are known as the independent values, and whichever variable it is for the domain set, typically it's going to be x. Then the x variable in that case is called the independent variable. And the y values, which are in the range set, those are the output values of the function. The y variable is known as the dependent variable. Honestly, because every value of y in the function is dependent upon the value of x. X is never dependent on y. Y is understood to be dependent upon x. It's a one-way relationship going from x to y. You're always going from the domain to the range, from x to y, from the input values to the output values, from the independent variable to the dependent variable. Many different ways to essentially say the same thing. Now, right at the beginning, you see here on the page at the top the word relation is in bold letters. A relation is just a mathematical rule of between two different variables. So it's some kind of relationship between two variables, say x and y. And there's no limits, no restrictions on this relationship. You can have the same number over and over again in the x set in the domain. You have the same number over and over again in the y set in the range. No restrictions of any sort. So you could have a random set of points plotted on the coordinate plane anywhere you want. They can be on top of each other, next to each other, any which way, and that could be a relation. But you may recall with a function there is a limitation. A function is a particular type of relation that follows a simple rule, which is that for every single value in the input set in the domain, every single value of x, if you will, there is one and only one value of y. So given that you know how much your x value is, there cannot be two or more choices for y. There must only be one choice for y. Now, it's okay if two different values of y correspond to, or the same value of y corresponds to two different values of x. So for instance, if x was 2 and y was 3, and x was 4 and y was 3, that's not a problem. You could even have the horizontal line y equals 3. So y is always 3, no matter what x is. It's a horizontal line, y equals 3. So for every value of x, y is always 3. That is actually okay. A horizontal line, for instance, y equals 3, is a function. It obeys the function rule that for each value of x, there is only one value of y. Now, where the problem comes in is if you have, for any single value of x, you have more than one value of y. So for instance, a vertical line doesn't work. If you take the vertical line, for instance, x equals 2, and I'm wishing I could show you this on the iPad, and I just can't right now, so attempt with me to visualize the vertical line x equals 2. That's a vertical line 2 units to the right of the y-axis. It's parallel to the y-axis, going up and down. Intercepts the x-axis exactly at 2 and goes straight up and down. Now, for that line, for every single value of y on that line, they all have the same value of x. So when x equals 2, y is literally every single real number. Negative numbers, positive numbers, and 0. So when x equals 2, y equals 0, y equals 3, y equals 17, y equals negative 5. So you have that one x value mapping to multiple y values. So here's the point. A vertical line is not a function, because you have the same x value going to more than one y value. So that disqualifies that particular relation from being a function. A vertical line is a relation. It's a set of points, so it's a relation. But it's not a function. A horizontal line is a function, and here's a good point, class. Every single straight line that you can graph on the coordinate plane is a function except for vertical lines. So a slanted line, a line with, or a horizontal line, those are functions, because for every single value of x, there's only one value of y. The only exception is a vertical line. It's not a function. Which brings us to the simple point, which I trust you all have heard this somewhere before in a previous course, what we call the vertical line test. The vertical line test. This is a very useful test. It's actually in your text. Okay, it is in your text, but it's actually mentioned in the next section, but that's okay. We'll talk more about that specifically on Wednesday, but okay, let me get this situated here. Yeah. But the vertical line test, as you'll recall, means if you graph the function, that if there's any point anywhere on the function that you can draw a vertical line that intercepts the function, if for any given value of x it ever anywhere intercepts the function at two or more places, then it's not, intercepts the graph at two or more places, then it's not a function. As long as it only intercepts the graph in one place, everywhere, for every value of x, then it's a function. That's the vertical line test. All right, so let's look at some options here. For instance, this two sets of numbers in these two boxes here on the screen. The left box has the various different times of day, the hours of the afternoon, and the right box has various temperatures in degrees Celsius. And the box on the left is our domain set for a certain function. The box on the right is a range set. So our input values are the time of day. Our output values is the temperature at each of those given times. And I trust you understand that at any particular time of day, at any single spot, of course, there's only one temperature. There's no variation in the temperature. It's just one temperature. So this does qualify as being a function. So at 1 o'clock in the afternoon, you see that that maps over to 9 degrees Celsius. At 2 o'clock, 13 degrees Celsius. At 3 o'clock, 15 degrees. I'm sorry. Yeah. And at 4 o'clock, it's still 15 degrees. 5 o'clock, it drops to 12, and 6 o'clock drops to 10. Now, these are Celsius temperatures, so it's not as cold as we're used to thinking in Fahrenheit. But this does qualify as being a function. You might observe that at both 3 o'clock and at 4 o'clock, it's the same temperature, 15 degrees. But that's okay, because for any single hour of the day, it only maps to one temperature. It's okay that for two different hours of the day, they both map to the same temperature. That's okay. So you can repeat a value in the range set, but you cannot have the same value two times in the domain set mapping to two different values in the range set. That's what you cannot have. So that qualifies as being a function there. And here's a nice summary at the bottom of this first page, 87, of the characteristics of a function which translates us from set A to set B. First of all, every element in the domain set, the input set, call it set A, has to be matched with an element in B. What does that mean? That means that you have no element in the domain which doesn't match to anything. Then if that's the case, if you've got an element in the set you're calling your domain set and it does not match, you got an X value and it doesn't even have a Y value, then obviously you don't have a point on the graph. The function does not exist at that particular X value. So here's the point. That X value is not in the domain of the set. You have to correct your domain and eliminate that number from the domain of the set. So to qualify to be in the domain set, every element in the domain set has to match to one and to only one element in the range set. Okay, second point. Some of the elements in the range set B may not be matched with any element of A. This is a very technical point that I don't want to make a big deal about, because typically we call the range set the set of output values, the set of Y values for the function, and that's generally how we're going to use that term. Technically, the range set is just a set of values out of which we can select the output values, but that's a technical point that I am really not going to pursue. Generally speaking, loosely speaking, we say the range set is the set of output values, the set of Y values for any particular function. That's loosely how it's generally spoken of. So the third point, two or more elements of the input set A, the domain set, may be matched with the same element in the range set. the output set of values, B. And we looked at that right above here. That, for instance, is the case where with the time being 3 in the afternoon or the time being 4 in the afternoon, both of those map to the same temperature of 15 degrees. Well, that's an example of characteristic 3, that 2 or more elements of A may be matched with the same element of B. And of course, this is the last one. The fourth point is the one I've been making a big deal about. An element of A, the domain set, the set of input values, cannot be matched with 2 different elements in the range set, the set of output values, set B. It can only be matched with 1. So characteristic number 1 says it has to be matched with 1. Characteristic 4 says it cannot be matched with more than 1, which boils down to each element in A must be matched with exactly 1 element in B. 1 and only 1. On the next page here, testing for functions, you're going to have some homework problems where you're given tables of values like this, tables for X and Y, the input values and the output values, respectively. And for instance, this table right here with the input values of 2, 2, 3, 4, 5 and the output values of 11, 10, 8, 5, and 1. And they've gone ahead and plotted those points for you, which is nice. And what you see here is that for the same value, I'm sorry, no, the plotting is not this. That table of values is going to create a problem because for the same input value of X, you have the 2 different output values of Y. The first time 2 plots to 11, the second time 2 plots to 10. So you have the XY ordered pair of 2, 11 and one of 2, 10. They're right vertically on top of each other, so to speak, one unit above the other one, exactly vertically above it. So that violates the vertical line test. So this table of values given to us in example 1a is not a function. It does not describe Y as being a function of X. But the graph that they give you in example 1b, those 5 points plotted there, that is perfectly fine to be a function of X. And by the way, it's okay that the points are not connected. They do not necessarily have to be connected as we generally draw our graphs. You can even just have independent separate points like that. As long as no 2 points are stacked up vertically one above the other one, then it's okay. You do have a graph that is describing Y as being a function of X, so it is a function. Okay, what if you're given some equations as example 2 here does for you? The equation x squared plus y equals 1. Well, let's do a little algebra on that and solve for y. Let's get the y by itself on the left side. It's easier to see what's happening. So when we subtract x squared from both sides, we get y equals 1 minus x squared. Well, that turns out, class, to be a parabola. It's a downwards opening parabola with its vertex right on the y-axis at the point 0, 1. Its maximum point is right on the y-axis where y equals 1. And then it goes down to the left from there and down to the right from there. And the good part about this one is for any single value of x, there is only one value of y. Because no matter what number you put in for x and then you square it times itself and then subtract it from 1, you're only going to get one value of y. So that equation, x squared plus y equals 1, does represent y as being a function of x. Yes, it does. Now the second one, example 2b, negative x plus y squared equals 1. This one is quite different actually. When we now attempt to solve the equation for y by itself, here's what we do. We add x to both sides, as they're doing right here. Add x to both sides, so then we get y squared equals 1 plus x. Now to solve for y, you can't just subtract something or divide by something. You have to take the square root of both sides of the equation. And if you recall, whenever you take the square root of both sides of an equation, you have to introduce the plus or minus sign. So the square root of y squared, we can just call it y. It's actually plus or minus y, but we'll just go with y. And then the square root of the quantity, the right side of the equation, 1 plus x, turns into, it can either be the positive square root of 1 plus x or the negative square root of 1 plus x. So in this case, for every single value of x for which the square root of 1 plus x makes sense, you're going to get two values of y. For instance, if x equals, say, negative 3/4, then 1 plus negative 3/4 is the same as 1 minus 3/4. So you have the square root of 1 minus 3/4, which is just 1/4. And the square root of 1/4 is 1/2. And so y equals plus or minus 1/2 if x is equal to negative 3/4. But wait a minute, we've got a problem there. If x is negative 3/4 and y can either be positive 1/2 or negative 1/2, that violates the vertical line test. You got two different y values for the same x value, two different output values for the same input value. Cannot have that. So that's not a function. Okay. Let's talk about function notation. On to the next page here. I haven't used the text because, like I said, my iPad is unfortunately not interfacing with a computer today. Hopefully we can fix that by Wednesday. So, function notation. We have the name of each function. Every function is going to have a name, and typically that's going to be a small letter of the alphabet. And then those, generally speaking, are either F, G, or H. Very, very often the names of your functions are either going to be F, which is short for function, or the next two letters in the alphabet, G or H. Very often our text is going to use any one of those three small letters, F, G, or H, as the name of the function. Now, then, as you've seen before, I'm certain, we will use F parentheses x, which we will read out loud as being f of x. F of x. That is not the name of the function. When we say f of x, that's the output value of the function at the value x. So the f of x is actually being equal to the output value. Actually, f of x then equals y for any individual value of x. So when we say f of x, it's the same as saying y. F of x means the output value of the function when x equals some particular number. So we can have our function rule, for instance, saying something like f of x equals 1 minus x squared, like they do, or f of x equals x, or f of x equals 2x, or f of x equals 3x minus 5, or whatever kind of function rule you want to have. Then you can input various different numbers in the parentheses for x. For instance, say if x is 1, then we would say f of 1 and input the 1 in the parentheses. I wish I could show you this on the iPad, but say f of 1 equals, and then plug in 1 for the x in the expression. So for instance, this expression they give us right here, f of x equals 1 minus x squared. Well, then f of 1 would be 1 minus the number 1 squared. Well, 1 squared is 1 times itself, so that's 1, and 1 minus 1 is 0. So for this equation, f of x is equal to 1 minus x squared. F of 1 equals 0. F of 2 means you're asking what's the output value for this equation, how much is y when x is 2. So then you do f of 2 equals 1 minus the number 2 squared, which of course is 4. So 1 minus 4 is negative 3. So f of 2 would be negative 3. And as they do down here, what if x is a negative number? For instance, what if x is negative 1? Then f of negative 1 is, as we do it up here, 1 minus negative 1 squared. Well, negative 1 squared, that's negative 1 times negative 1, and negative times negative gives us a positive, so it's 1 minus 1 again, and once again that's 0. So when x is negative 1, y is 0, f of x is 0, just as it was when x was positive 1, y was 0. But that's okay. It's two different values of x giving us the same y value. So that's not a problem. For this equation up here, f of x equals 1 minus x squared. If x happens to be 0, then f of 0 is 1 minus 0 squared, which is 1 minus 0, which is just 1. So when x is 0, y is 1, and we can accurately say f of 0 equals 1 for this function, f of x equals 1 minus x squared. So again, very key point here. It's sort of a subtle sounding point, but it's very important. The name of a function is a single small letter like f. But then when we say f followed by the parentheses x, and read that out loud as f of x, that's not the name of the function. That's actually a certain number. It's the output value of the function at the input value of x. And this can get a little bit more interesting, like this example 3 down below here. If you have now another function, the name of this function is now g, the small letter g, and they say let g of x equals negative x squared plus 4x plus 1. Well, this is a good function to use to give some examples of how to calculate these g of x values. If x equals 2, then you can see they're calculating g of 2 in example 3 part A, and so you plug in 2 into the function expression, the function rule. For every single place where you see an x, you plug in a 2. So it becomes the fact that g of 2 equals negative 2 squared plus 4 times 2 plus 1. So it's negative 4 plus 8 plus 1, which turns out to be 5. So g of 2 is 5, which means, class, you have the point 2 comma 5, the ordered pair 2, 5, is on the graph of that g of x equals negative x squared plus 4x plus 1 equation. Well, the next one looks a little bit different. Part B of example 3 is calculating how much is g of t. Whoa, what does that mean? That means you're introducing a third variable here, t, and you're saying let x equal t. So that means we don't know exactly what number x is. X is going to equal the value of another variable equal to t. So still follow the same procedure. Plug in t for the x and simplify. So g of t is understood to be then negative the number t squared plus 4 times t plus 1, which is negative t squared plus 4t plus 1. And that's the actual answer. G of t equals negative t squared plus 4t plus 1. All right, part C. What if x happens to equal x plus 2? Well, this is what we're going to be looking at here in not long after today. We're going to be looking at this. This is actually a horizontal translation of the function. But when you plug in x plus 2 now for x, that means g of x plus 2 is equal to negative the quantity x plus 2 in its entirety being squared plus 4 times the quantity x plus 2 plus 1. And so you actually have to multiply out the x plus 2 squared, becoming x squared plus 4x plus 4, still with the minus sign in front of the whole parentheses, plus 4 times x plus 8, and still plus the 1. And so the three terms x squared, 4x, and 4 all go negative here with the minus sign being applied to them, plus 4x plus 8 plus 1. And finally simplify by combining like terms. And we find out that g of x plus 2 then actually equals negative x squared plus 5. All right, now the rest of our time together, I want to talk about specific types of functions, 4 specific types of functions: a linear function, a piecewise function, the absolute value function, and a square root function. And so to discuss the linear function, I'm going to take us back to page 87. A nice little box here on page 87 in your text. It's the first of several what your text calls parent functions. Functions which you can make variations on, and yet they're still similar to the parent function. And this first parent function is the linear function. These, of course, as you've seen before, this is where when you graph this function, if you graph these equations, you do get a straight line. And the parent linear function is simply f of x equals x, or just simply y equals x. And that's an interesting line because every single point on this line, the y coordinate is the same number as the x coordinate. They're always the same number. So if x is 2, y is 2. If x is 7, y is 7. If x is negative 3, y is negative 3. Because y equals x. That's what it says. The y value equals the x value. So in function notation, we write this as f of x equals x. And it graphs very nicely as a slanted line with a slope of 1. It goes through the coordinate plane at a 45-degree angle, halfway in between the x-axis and the y-axis. A 45-degree angle from the x-axis and a 45-degree angle away from the y-axis. And now let's start talking about the terms domain and range a little bit more. The domain, again, is the set of all possible input values for the x variable. And looking at this line right here, of course, the graph, as it's illustrated here, stops and appears to stop at both ends, but that's just the page space here is limited. It is understood that this line actually goes literally forever on upward to the right, forever, without end, boundless, limitless, and goes forever down to the left, forever, never, never, without end, never stops, never ends, which means that as we go horizontally to the right along the x-axis with increasing x values, or horizontally to the left along the x-axis with decreasing x values, we never get to a point that we're past the line. Well, got too far out now, we're past the line. No, that's not going to happen. So no matter how far you go out with x to the right or to the left, you never get past the line. It's always an x value that's going to have a point on the line. So the set of x values that work for this equation is limitless. It has no bounds. And so the way we say that is the domain, the set of x values, is this set of values expressed here with this interval notation, parentheses negative infinity, comma, positive infinity, and close of parentheses. The parentheses indicate that this is an interval that's open-ended. And it sort of looks like an ordered pair. Unfortunately, it's the same notation that's used in math for an ordered pair or for an open-ended interval. Very same notation. But this is not an x and a y coordinate. That's not what this is. It's what's known as an interval, and it's not an x. It's not an ordered pair. So what this domain interval tells us is x can take on all the values all the way going down to negative infinity, all the way going up to positive infinity. A way to say this, class, in words is that the domain of this function is all real numbers. The domain is all real numbers. I trust you've heard that expression before. Well, similarly, as x increases boundlessly off to the right and goes boundlessly off to the left, well, y also is boundless, because as x increases, y also increases. As x decreases, y decreases. And so the range of this function, the set of all possible y values for this line here, is also boundless, has no limits. So the set of y values, which is the range, is from negative infinity to positive infinity. In this case, the domain and the range of this function are expressed the same way, but the domain notation, negative infinity to positive infinity, is for the x values. The range notation of negative infinity to positive infinity is for the y values. So vertically, this line goes up boundlessly forever and ever, and goes down boundlessly forever and ever. That's the range. This line only has one intercept. Its x-intercept and its y-intercept are the same point. The point 0, 0, which of course we call the origin. The last little element of this box, it says the function is increasing. We're going to talk much more about that in the next GoToMeeting or two. But to say that it's increasing simply means that as x increases, as x gets larger and larger, y also gets larger and larger. It doesn't tell you how fast it gets larger and larger. It's just that it's getting larger. So as x increases, for instance, from 0 to 1 to 2 to 3 to 4, well, y increases too from 0 to 1 to 2 to 3 to 4. So y is also increasing. So since that's what increasing means for a function, if as x increases, what's happening to y? Is it increasing, or is it decreasing, or is it staying the same? Is it staying constant? Well, in this case, it's increasing. So therefore, we say the function is increasing. At the bottom of this box is also another important point. If you have a horizontal line with slope equal to 0, for instance, y equals 2 units above the x-axis, and just a horizontal line with a slope of 0, then since the y value is the same for every single point on that line has a special name also, and it's called the constant function. So if y equals 2 or y equals 17 or y equals -5, equations like that graph to give you a horizontal line, when we say, instead of y, if we replace it with f of x, if we say f of x equals 7, f of x equals 17, f of x equals -5, those are examples of constant functions. Okay, the next type of function I want to talk about then with you, the second type, is what's called a piecewise function. And some of you have seen this before, but I suspect perhaps some of you have not. A piecewise function is a little bit tricky because it has two or more different function rules. Generally speaking, that means for us in math, it's going to have two or more different equations, depending on how much the x values are. So that means if x is one set of values, you got this one function rule for f of x. If x is a different set of values, you've got a different rule to find out how much f of x is. And here's an example right here, example 4, piecewise defined function. Here's the rule. It's f of x equals these brackets now. F of x does equal x squared plus 1 only if x is less than 0. So that's for negative values of x. However, if x happens to be 0 or happens to be a positive value, your function rule then is f of x equals x minus 1. Quite a different rule. And when you have piecewise functions like this, you can get graphs as down below here. When x is less than 0, you have this half of a parabola right here, x squared plus 1, for those values of x. And over here on the right side, if x is positive, you have a straight line. F of x equals x minus 1. Straight line. So that looks strange, but that's actually okay for a piecewise function. And what gets interesting about these is, for instance, do the two portions of the function actually meet at their point of juncture, or do they not meet? And for instance, these two do not meet. You can see the x squared plus 1 part is coming in from the left and comes into the y-axis right here at y equals 1. But the straight line is coming down from the right, and it's approaching the y-axis and finally gets there when y is negative 1. Now, another interesting point is this straight line portion actually comes down and meets the y-axis at negative 1, because, notice the rule, f of x equals x minus 1, not only when x is greater than 0, but also when x equals 0. So that means the y-intercept of this function, you plug 0 into x minus 1, then f of x is negative 1, or f of 0, let's say, is negative 1, so the y-intercept of this function is actually negative 1. It is not positive 1. And again, let's look at that. Why is it not positive 1? Because the first rule for this function for negative values of x is exclusively for negative values of x. It's not for x less than or equal to 0. It's only for x less than 0. And so there is no point stacking on top of points. You don't have a point on the y-axis at y equals 1 and a point at y equals negative 1. The way you would graph this class, perhaps you remember, at the point y equals 1 up here, you would actually graph this. We'll look more at this on the Wednesday go-to meeting. You would graph this point with a hollow circle, and you'd graph the point down here at negative 1 with a solid circle, indicating that point is included on the graph, and the hollow circle up here at y equals 1 indicates that point is actually not part of the graph. Okay, so that's how piecewise functions work. You're going to have, I think, a couple of homework problems with those. The third type of function then is a type of function that can actually be expressed as a piecewise function, and that's what's known as the absolute value function. I trust everybody recalls absolute value, the idea that the absolute value of any number is that number positive. So if you've already started with a positive number, the absolute value of that number is just itself. It's also true that if you start with the unique number 0, I say unique because that's the only number that is neither positive nor negative, the absolute value of 0 is 0. So for any positive number, its absolute value is itself. For 0, its absolute value is itself. However, for every negative number, the absolute value of every negative number is that number positive. So, for example, absolute value of 7 is 7. The absolute value of 3.5 is 3.5. The absolute value of 0 is 0. But the absolute value of -1 is +1. The absolute value of -2 1/4 is +2 1/4. And here's where it gets a little interesting, class. Since for every negative number, the absolute value is that number as a positive number, that is, that positive number, here's where, like I say, it gets interesting, is actually the negative of that negative number. What do I mean by that? I'm saying that the absolute value of -2 1/4 is actually the negative of -2 1/4. Because the negative of any negative number, you're taking the negative of a negative, that's the same as a negative times a negative, gives us a positive. So what that enables us to do, class, is to represent the absolute value function. Here it is. Remember those vertical bars around x to represent absolute value. If we say the parent absolute value function is f of x equals the absolute value of x with the bars around the x, then that actually can be expressed, drop the bars around the x, and express that function then as a piecewise function with two different rules. And here's how you can do it. F of x equals the absolute value of x can also be written as f of x equals, and with the brackets here now, it simply equals x itself as long as x is greater than or equal to 0, or it equals -x if x is less than 0. And that's really what we've just been talking about. And now it's written down in math notation with symbols. So the absolute value function is exactly the same as the piecewise function for all positive values of x, and x being 0, that y is simply x, just like the identity function. However, if x happens to be less than 0, then y is the negative of x, but since x itself is negative, the negative of a negative gives you a positive. So we always stay either on or above the x-axis with the graph, and we get this interesting V-shaped graph right here. F of x equals the absolute value of x. From both the left and from the right, it's coming down and meets the x-axis and the y-axis also at the origin at 0, 0. And then whether you go to the right for increasing values of x or go to the left for decreasing values of x, the graph goes up. Y is going up. It gets greater whether you go to the left or you go to the right. And that means that the domain of the entire function is unlimited. X can go as far as you want to the left, as far as you want to the right, no limit, unbounded. So the domain is -∞ to +∞. The range is quite limited. Notice the range, y can only come down to 0. Y never goes negative, not with the absolute value function. There is no real number that has a negative absolute value. There's no such thing. All absolute values are either positive or 0. So the range of the absolute value function, here's how you show it. From 0 to infinity, we keep the rounded parentheses around infinity because infinity is not a specific number. It's just a concept of a boundless number. But 0 is a specific number, and 0 is on the graph. Y equals 0. It's the point 0, 0. Yeah, that's on the graph. So we make this square bracket here instead of a rounded parentheses. The square bracket tells the reader that the range starts at the number 0 and includes the number 0 and increases then boundlessly to positive infinity. If we were to put a rounded parentheses to the left of the 0 instead of the square bracket, then that would tell the reader the range comes down to 0 but does not include 0. Then the one and only intercept, the x-intercept and the y-intercept are the same point, the origin 0, 0. The function, however, is not now either decreasing or increasing everywhere, but it is decreasing when x is less than 0. So on the open interval from negative infinity to 0, approaching 0 but not including 0, the graph is coming down. The slope is downward. But then once you pass the origin, the slope is upward forever, so we say that graph is increasing on the open interval from 0 to infinity. Again, we're going to talk more about decreasing and increasing on Wednesday. Then the last one I want to show you here today is the square root function, and that's on the very next page in your text, page 101. And here's where we do f of x equals the square root of x. In other words, y equals the square root of x. And I trust you've seen this graph before. It starts at the origin 0, 0 and then goes up to the right, gradually going less steeply and less steeply upward as it goes to the right forever. It never levels off, but it always goes up to the right. So its domain is from and including 0 to infinity, with a square bracket to the left of the 0 and a rounded bracket around infinity. So x values are anywhere from 0 upwards without limit. And y values are anywhere from 0 upwards without limit. So the range and the domain both the same, from and including 0 to infinity. Again, it only has one intercept. The x-intercept and the y-intercept are the same point, the origin 0, 0. And everywhere this function exists, it's always increasing. It's always going upward to the right. So it's always increasing. I want to share one more point with you, and we will talk much more about this tomorrow. The implied domain of a function means the domain is understood and implied from the very function expression itself. It may not be written out in words, but the reader understands the domain is limited based on the function rule. The two major ways, the most common ways that domains are limited for functions has to do with those particular values of x that are excluded because it would make the denominator be equal to 0, which means then the fraction would be undefined, so the function itself is undefined at those values of x, which means when the function, if we say a function is undefined, it means the function does not exist for those values of x. So for instance, for f of x equals 1 over x squared minus 4, if x is either positive 2 or if x is negative 2, either of those numbers times themselves gives us 4. And of course 4 minus 4 gives us 0. And 1 divided by 0 is impossible. So the f of x would be undefined, which means that the two numbers, positive 2 and negative 2, are not in the domain of this function, f of x equals 1 over x squared minus 4. It is a legitimate function. However, its domain is not all real numbers. It's literally, the domain is all real numbers except the two numbers, negative 2 and positive 2. Still has an infinite number of values of x in its domain, but it does not have negative 2 and it does not have 2. And we know that simply by the function rule, because if we were to plug in either of those numbers, negative 2 or positive 2 for x, the denominator would be 0, and we can't have that. So that's one type of limited domain example. The second major type of limited domain is when you have a square root. Because just as down below here with the square root function, please notice that the function does not exist to the left side of the y-axis. It's just not there. So that's because, as you know, we cannot take the square root of a negative number and end up with any real number. Yes, you can get a complex number, which we will study later in this course, but you cannot get a real number as the square root of any negative number. So, therefore, it is understood as the reader looks at this square root of x expression, I cannot input any negative number in for x and output a real number. So therefore, the domain can only start at the number 0, x equals 0, and increase from there. So the domain is the number 0 and all positive numbers. And therefore, the domain can be expressed, as it is right here, a square bracket to the left of 0, comma, infinity, parentheses. That tells the reader it's every number from and including 0 upwards without bound forever and ever. And similarly, just as x can go boundlessly to the right, y goes boundlessly upwards also, so the range is the same set, from and including 0 to infinity. And this function is increasing everywhere it exists. That is, from x equals 0 all the way to infinity. We'll talk more about the technicalities of this in the next lesson, I believe it is, where we will explain why it doesn't have a square bracket on 0, because intervals of either a function being increasing or being decreasing are always on open intervals, not closed intervals. So we'll talk more about that next time. So this is our discussion to introduce the rather complex subject of functions. We'll be using functions the entire rest of this semester. So this is our introduction to it, and I wish everybody well on your homework. Please remember this section 1.3 homework is due Tuesday evening, September 1st at 11:59. The next homework will be due Thursday. The 1.4 homework will be due Thursday evening, September 3rd, and we will have a GoToMeeting about that at 3 o'clock Wednesday afternoon. And I'm about to close out this meeting here, and then it takes approximately 45 minutes, give or take a little bit, to process these things. Sometimes it takes longer. I've seen it even take up to an hour and a half, but usually around 45 minutes. And then I can upload the formatted video into YouTube for you, and I will send out an announcement, as always, with the code numbers, the URL, so you can access the video and watch this. So, have a good day, everyone. And as always, please contact me if you have any questions. Send me an email or come visit me or call, whatever works best for you. Email is a good way because I'll catch that for sure and get back to you. So have a good rest of the day here, and I'll see you next time.